All right. This is for you, Shelby. Only you. It's the only reason we're doing this. Just you, Shelby. All right. So the hammer problem, you can see we pulled back, and I like this problem for the fact that it's an everyday problem. You probably have grabbed a hammer sometime in your lifetime. If not, you will, I would assume, and pull back on it to pull a nail out. So you can see where you pull back on the 150, and even though it's shaped a little bit differently, it's still just a first-class lever. So you pull back on one side, the other side goes the other direction. You can see where I have the fulcrum down here, and I just set up the torque, force times distance, the 150 times the 30 here is equal to the 5 times the X over here. Now that's clear, it gives you 900. Here's the key though. This X is perpendicular right there. And as you know, torque, when you just do force times distance, you need a perpendicular, they need to be perpendicular. And they are. So the 900 comes out to that perpendicular force that I have marked X. That's the key to get started here. Then I drew a picture to do the trick. I left that out of the, I think it's easier just to look at the 900 and then say, okay, now let's do the trig now. So far questions, the 900, F times D equals F times D. Then the nail is being pulled up. If you look at the picture in the book over here, and it's just trig. Just do SOHCAHTOA or your trig shortcuts to get the numbers here. So I make a right triangle. I do it like this. I make a right triangle there at the opposite side. That's the third side because that's a 60. Do you remember your shortcuts? Heck no. Yeah. So you're dividing that by a square root of 3. I don't remember what that number is, 519 or something. Kind of lost it. There it is, 519.62. So that'll give you 519.62 for this one, which is the same as down here. The decimal point, 519. And then the other one, the hypotenuse comes out to be 1039.23. 1039. What did I say it was? 23? 238. And if you look at the picture in the book, the nail, this is the nail down here. That's the nail down here. So you're pulling up to pull the nail out. So you're pulling the 1039.23 newtons. So it's a general torque problem and then a little bit of trig. This is the answer right here for A. I think they put it in kilonewtons, right, Ron? So it would be 1.04 kilonewtons. Then this is where it gets, I don't quite get what they have. Then they ask for, let me read it so I get it right. The force exerted by the surface on the point of contact with the hammerhead. So they're talking about here. That's what we were been calling R. I feel like it's pushing up and to the left right there. But the book takes the 150, this one, and this one, and they subtract them. That's where they get their X component to that R. I don't quite get why they subtract them. Anyone see it? Why you would subtract them? I don't see it. So I can't explain it if I don't see it. Lily, do you see it? Bert? So I think, what is that if you subtract 519 minus 150? What's that give you? Calculator. What, Brian? You're a calculator. I could do it, but I'm. Say it again. Yeah.
369.6.
Okay, I think they make this 520. So it would be 370 then. So they get 370. So they say that this has two components, but they say it has a 3. Is it positive or negative? They say it's 370 by subtracting those. And then I think they just have the 900 for the other ones. Isn't 900 the second answer?
Yeah.
900J. So you can see where that one comes from. So that would mean that their answer here is positive, positive. They're saying that this R is in this direction and this direction. Like that. So that's how they get it. But they subtract, you can see they subtract the 150 and the 519. That's the part that tricks me a little bit, why they subtract those.
Was because technically like the 30 would be upside down. The Yankee gives like a pull up the floor, so technically we go down. the other way.
Yeah.
Up and down. And then
Yeah.
we subtract the block, the extra pad. And then,
Yeah, but even so, if you talking about like this,
yeah,
but the 519 over here is pointing to the left and the 150s to the right, I still see that there's a difference to the left. Like this would be negative over this way. Like I think it would be over this way. But that's why I'm not sure if they just have a mistake or I just don't quite get it. So, but that's how they get the 370, no big deal. They're talking about the support of this, and if you're pulling on this hammer this way, I feel like the surface of the ground, this surface here would be supporting the hammer back in the other way. It's just what I'm feeling. Because you don't pull this down into the, like this is some type of surface here. You don't pull it through the surface, it's supporting back up the other. That's what I say. Something for you to think about. If you come up with a good plan, let me know. Not going to spend much more time on it, but that's where the numbers come from. Sorry, I don't have the exact solution. All right. Was there anything else that you needed to go over before I show you the new example? Huh? 12? What's 12? Oh. So we have, it's just straight out there, bar comes out here, then there's a force hanging down there. So is it asking for the tension? I don't remember. Here. So this is just what we did in the lab yesterday, but they don't give you the distance. Was that the problem we had yesterday, Ryan, when we were talking about this? So you can call this distance D or X or whatever you want it to. What do they give you this weight? 20 kilograms, which is 2 times 9.8 is 196 newtons. Does that sound right? And the question is asking for torque. So I would do, you can go back and do it like chapter 5, or staying with this chapter, we would do counterclockwise torque equals clockwise torque. And our tension here has 2 components like that. And this will be our T. Do they give an angle? 30 degrees right in there. So if there's 30 degrees there, this one is T sine 30, or you could call it TY the way I did it the first day, and this is T cosine 30, or you could call it TX. And it looks like the torque's going to be T sine 30 multiplied by the distance all the way to the fulcrum, which is here, the pivot point. So you multiply it by X. And then that would equal what, the 196 the other way. And its distance to the fulcrum is also X. So the X's cancel. Does that give you the answer? What is the answer? Just dividing by 0.5 or multiplying by 2. So the tension will be 392. And then the other sides, the other side do it the same way we did R yesterday. Is there anything, did they ask for something over here?
He asked for the whole wall.
Exerted by the beam.
Yes, they wanted to.
So they want, they're asking for, hey, I want you to be blue. They're asking for these, the RX and the RY. Exerted on the beam by the pole. I think they're just asking for this. Did you do it? Is that all it is? RX and RY? It's just RX and R1. What? The J zero because
That'd be T sign, that's why I said, because T sign 30, the TY, the 196 cancel each other.
what is the TY? It's 196, right?
Yeah. So we go with the forces.
Yeah, but why?
Yesterday, you said because it's directly below.
Because this is directly below that.
That's what you said.
I was making that up, Bryce. What about it? The X is just the distance to get the torque. Did that work for the RX answer?
Yeah.
Oh, yeah, the RX will be equal to the T cosine theta. And it looks like the RY plus that should equal the weight of that. And I don't see why, I don't know. I don't know why it doesn't. I didn't even think about that.
That's what I thought was like, how do you get this?
If you did the RY plus that.
Say it again.
If you did the RY plus 196 equals 196.
Oh. RY up plus the 196 up is equal to the 196 down. Oh, that's zero. That works. Told you I don't feel good today. Dumber than usual. Okay. So it's just a normal, and then the RX is a T cosine 30. Okay. Anything else? Is that all I gave you? What's the question?
Why do we do
Up, this is up equal down. This is all the ups, equal all the downs, forces. RY and TY are the ups. Down to this one. Let me go back and show that. I guess it's not very clear, so I'll show. So this is your TY right here. So the RY plus the TY are the ups. And then the down is just the weight of the thing, which is the 196. So that TY is that 196. Does that help? Yeah. Sorry about that. Sorry about that. Any other questions? Okay. Well, today's example was actually pretty easy. I simplified it. Instead of making a big problem out of small, you'll still get the same idea. So this is the bridge problem example. Just want to copy it down real quick. Pause this. Recording, okay. So we have Eamon standing on, this is called the bridge. He's standing on a bridge. It could just be a 2x4, it could be a plank, it could be anything. You'll see we'll treat many problems using this solution. Even a car, how much force is on each wheel of a car, if we have a problem like that. But for this, it's just, I call this pier A or support A and support B. And Eamon's standing there, and you can see that he's not centered. It is a uniform bridge of 400 newtons. So we know we can go to the center of the bridge and put the 400 Newton force there because it's uniform. It says the bridge is, did I get the, 10 meters long? That means that we have 5 meters from each end for the 400. Everyone okay with that? It's 5 meters from each end. Now remember, for torque, we are only concerned about the forces, the distances to each fulcrum. So we are going to treat this like a second class lever. So to find the force on A, did we even go over second class lever with you? This is the second class lever. It's like a wheelbarrow. I know we did it last year. And we have a 600 Newton dude here. So we have 600 Newtons here. We have 400 Newtons over here. This is what we're looking for, the force on A, that arrow pointing upward. And the picture is deceiving because when I solve this, we're finding the force on A, but look what support is in the picture. Do you see how B is the one in the picture? So the fulcrum we're using is B, but we're on this end looking for A. You can look at this as like grabbing a wheelbarrow and picking up the handles over here. This will be the wheel over here. And how much force would it take to lift up on this? That's how much force A is supporting. So we're looking for this force over here, and it's just a torque problem now. Counterclockwise equals clockwise. I'm going to do the clockwise first on this one, or total torque equals 0. Let me write that. This is total torque equals 0. I like to say clockwise torque equals counterclockwise. So I'm going to clockwise first on this one because that's what I'm going to write first. Clockwise torque equals counterclockwise torque. So force times distance. The clockwise, you can see that if this was, I'm certain that you can all picture this, but let me grab this and show you anyway. If I had this here and I lift up on the handle here, you can see how it's rotating it clockwise. So the FA times the distance often left out. How far is this from the fulcrum? It's all 10 meters. The other two forces are trying to spin this, you hold this on B down, it's pushing it down counterclockwise. So we have 600, you know what, let me put those distances on there before I go any further. This was 5 meters to the fulcrum. This one was 7 meters from the fulcrum. And this is all 10 meters from the fulcrum. And that's important that you don't use the 3 because we need everything measured to the axis of rotation. So F times 10 is equal to 600 times 7, being lazy on my units, and 400 times 5. Someone calculate that real quick. Guess I could do it. What is it? 620, that's right. So 62,000 divided by 10. So FA is equal to 620. So FA is equal to 620 newtons. That's the support on A. So the answer to the question, find the normal on each support. So the normal force will be right here. And that's equal to 620 newtons. And on the other side, now you have two choices here. You can just reverse the picture. And it would look like this. You draw A, come all the way over here and find the F on B. In fact, let's do that real quick. We'll do that. I'm out of room, so I'm going to switch the picture. So we have, what do we just have? We had A there. We had force on B there. Eamon's there. So now he's 3 from the fulcrum. The 400 newtons is 5 from the fulcrum. And this is all 10 from the fulcrum. And then we just set up the torque again. So we have the FB times the 10 equal to the Eamon was 600 times the 3, and then the 400 times the 5. Should be the difference from 10,000 to 600 or 1,000 to 620. So it should be 380. That come out 380. So the other support has 380. They're not balanced because you can see that the picture originally was not symmetrical because Eamon was off to one side. So the one where he is, if you look back there, oh, where were we? If you look back here, because Eamon's closer to A, there should be more weight on A, or it should be supporting more. So A, the answer was 620, and B, it was, what we say was 380. Now, I could have, the reason I was able to solve that so quickly in my head because we know that if FA is there and FB is there, if I want to look at this, up equals down, you could have solved the second one like this. Once you got this first answer, you could have said, well, there was FA is up and FB. It's very hard to write with this. I'm sorry. It's too sloppy. Probably used to this crap from last year. FA was up. FB, this will save you time. You don't have to do the whole second one. FA is up, FB is up, and then the 600 and the 400 are down. So we saw that this was 620. And you can see here, I just took 1,000, subtracted 620 and got 380. You could have done it that way instead of the way we did the second picture. So either way gives you the answer. Questions? That's it. Come on, where are you at?